Hello. In today's Mechanics of Materials session, we'll be solving a problem on stresses. An aircraft tow bar is positioned by means of a single hydraulic cylinder connected by a 25 mm diameter steel rod to two identical arm and wheel units, DEF. The mass of the entire tow bar is 200 kg and its center of gravity is located at G. For the position shown, determine the normal stress in the rod. So, an aircraft tow bar is positioned by means of a single hydraulic cylinder connected by a 25 mm diameter rod to two identical arm and wheel units. So this is the rod here. The arm and wheel unit is this. Because we are looking at it from the side, there's one on this side and one on the other side, and they're connected together by this by this rod. The mass of the tow bar is 200 kg and the center of gravity is located at G. So this here, center of gravity G. So for the position shown, determine normal stress in the rod. This is the rod, right? So assume the stress at this point here as the normal stress. Of course, for stress, it's the force over the area. Produce force over the area in that rod. Now it says an aircraft tow bar is positioned. So just to put things in perspective, aircraft tow bar is a strong metallic bar to move an airplane on the ground. So when the plane is probably on the floor or on the ground, basically, and you want to move it from one location to the other, they typically don't turn on the engines, right? For either because the noise of the engine is pretty loud, too close to buildings, to save fuel too, and also because engine blast itself is dangerous. So this strong metallic bar is made of high strength steel, which is made of high strength steel, is then connected to the tug, then used to push or pull the airplane closer to where the destination or wherever they want it to be on the ground, basically. So that's and from this diagram, if you can see this diagram, this is a wheel. Most likely either it can be the landing gear wheel or so, and this is the bar. So it clamps to this, then it pulls. In this case, probably pulling this way, pulling that way. And this is the tug bar itself, because this is its own wheel, because it requires its own wheel for it to move, where it clamps this. So for a problem like this, it says determine the normal stress in the rod. To determine the normal stress in this rod, we typically start for problems that involve stresses. For us to have a good analysis of the problem or good overview of the problem, we start by drawing the free body diagram. So for the free body diagram, so that's a schematic representing the tow bar. G, which is the center of gravity, is here. Of course, we know that its weight is acting downwards on it, right? Then you can see we have a joint here. You can see this joint here. You also have to represent this on the free body diagram. This point here. Of course, by looking at this wheel, you can see two forces here and here, right? So that also has to be represented on the free body diagram. A y, a x. That means that's the Cartesian coordinates basically here. Now on this tow bar, you can see that there's a wheel here, right? So let's take this. So the arm and wheel unit, DEF, it's here. Somewhere close to this point here. Yeah. Somewhere close to this point. Let's draw this like this. Okay, we have a D, we have point here D. Here we have F, where the wheel is at. Right. We have this wheel here. Pardon my drawing. So okay, let's go back. Yeah, we have that here. So because of the wheel we have here, there should be a normal reaction, R, right here. Then the other component here is B. It's more like a hook or a clamp, right? B here. So there's no, for this diagram, there's no force shown on that. So don't assume anything is acting there, right? So typically this is our free body diagram, FBD, our free body diagram. For a free body diagram to be complete, the forces and the direction have to be shown, right? So from point A, that's here, up to where the reaction force, 850 millimeters. Then from that point up to, that's from this same point A up to the center of gravity, it's 1150 millimeters. So here is your free body diagram. Now, for this question, the weight was given as W equals to 200 kilograms, right? So, of course, to find out the Newton, its weight equals to 200 kilograms times 9.81. Remember, that's in meter per second squared. So if you find the weight, that gives us 1962 Newton. That's the weight. Now the next part we are to now, of course, we have some unknowns, right? We know the weight here. We don't know the reaction. We don't know at this point A. We don't know the forces acting at it. That's A sub Y, A sub X. We don't know that as well. So there's a component of D, but let's solve this main component first. So for us to solve this part, we kind of let's make it like a single body. Take this of course is clamped to this, so we can easily solve this. So when we are done solving that, then once we have the reaction force, then it's easier to find the forces acting at this point. Okay. So in problems like this, you take moments. Now, taking moments is like the turning effect of a force, right? What that means is if you apply, let's say you want to understand how the forces at that point rotate with respect to any force applied to the object. That's what it means by taking moments. So let's see how the forces will rotate or turn an object about that chosen point. In this point, let's choose point A. So we're going to be taking moments. So take moments about point A. Now, if you want to take moments about point A, in terms of notation, what that means is the sum of all the moments about point A is equal to 0. Now, the convention will go anti-clockwise, right? Positive, meaning the turning effect of the forces. If it's anti-clockwise, we take that as positive, and the other way we take it as, and the clockwise we take it as negative, right? Now for this, if you take more, of course, effectively the idea of doing that is it eliminates the need of us finding the components of forces at point A. So if you take moments about this point, it's the same line of action, this. So this will be 0. There's no point taking that. Now, with respect to this weight, that's the weight of the tow bar, from this point to the distance from here up to here, right? So the weight multiplied by this. And since this and the effect of this weight will make it move clockwise, so that will be negative. Similarly, this is a reaction. It's acting upward. Want to cause this to turn, right? Turn anti-clockwise, which will be positive. So what I've just explained, I'll write that out. Now, the reaction force, it's so moments, it's force times distance, right? So the reaction force, which will be R, or let's write anyone is fine. We can write the force first, times the distance, 850. Let's make it clear. 850. That's this reaction force. This reaction force want to cause this to turn, right? That's positive. So 850. See the arrow. I mean, typically the arrow is facing up. It's positive. Down, it's negative. 850. Then minus the force. That from what the weight is 1962. We already calculated that here. Multiplied by 1150. Now equal to 0, because we no longer have any other force on acting on this. The only forces here are that's these forces. We have forces here, but the fact that we're taking moments about here helps to eliminate this to be 0. We have this 1, then this 2. There's no force here per se, it's just a connection here. I mean, as far as this problem is concerned. So if you evaluate that reaction, if you simplify this expression, the reaction force will be 2654.5 Newton. And that's the reaction force. So now we have the reaction force here for the problem. Of course, putting it in context, the reaction force is this one here. So we have this. Now, if we have this force, reaction force, because it's acting on this arm and wheel, right? Then any other force directly connected to that, which is like this one, at an angle, we should be able to compute that. So first we've done is find the free body diagram about this. Then next is to find the reaction force about, the free body diagram of this was able to help us get the reaction force. Then after that, we're then able to get this. We'll now be able to get this basically. So the next thing is the next thing will be the free body diagram of the arm and wheel units. So let's use a duplicate of this diagram. So now what we need is to have the free. So now the next thing is to sketch that's the free body diagram of this part. Now for that, just so I put this diagram so that we can use it as a reference. If we have let's get this line here. I mean, not a perfect diagram, but just to make it easy to understand. The reaction force here. The reaction force, which I previously calculated to be 2654.5 Newton, is there. Now, at this point here, see we have point E at this point, right? Point E, of course, it will have two components because we are using Cartesian coordinates, right? X and Y. So it will have two components, EX. Of course, there's EY. Yeah. There's EY. Okay. EY. Now, for this diagram, just let me clean this up to make it clear. At point D here, we have DC. There's a force here. As a result of that rod, DC. There is D and here is C. There is a force there. So force CD. Right. Now we have this one. There is. Okay, so if you look at this diagram here, look at this point here. If you have this rod here, there is an angle here, right? Look at this. Let's say here is C and here is D. It's the same thing, but just translating it. So if this here is alpha, then here will be alpha. That's the idea. Look at, remember, from alternate angles. If here is alpha, this point will also be alpha. Now this will help simplify the problem in terms of finding what this angle is at. Because if you have the force at an angle, then to have two components. Now looking at this, we have these distances here. They are very useful in finding these components, right? For instance, to find what this alpha is, we have, you see, if you look at this, look at here, from this point here to here is 100. Here's 100. And from this point, and from here, this line to this point is 675. So it's like having a triangle like this. 675 millimeter, 100 millimeter. And here we have alpha. So now to find the angle, what alpha is, if you remember from your trig, tan alpha, which is opposite over adjacent. This is opposite here. This is adjacent, right? Which is tan alpha is equals to 100 over 675. Tan alpha is equals to tan inverse of 100 over 675. We'll then get alpha to be 8.427. That's an approximation degrees. So we then have what alpha is. Now the point is, with this alpha here, which is the same as this, right? With this alpha, you can find what this component of what the x component of the force is and what the y component of the force is. That's the idea of that. Because once you have a force at an angle, then you can find the components basically. So for this arm and wheel, we have three forces on it. This is reaction force from the wheel, which is this reaction force from the wheel. This point E, because it's a pin, right? It's connected to a point here. So we have two forces here, the x direction and the y direction. Then D as well too. Can have two forces there basically. Okay, no, actually in this point we have one force because of this coming here, right? I mean, this point coming could be this way here. This is pulling, it's at this point. We have a force here due to FCD. And this FCD can have two components as well. So the idea is, since to simplify the problem, you have to choose where you take moments from. In this case, we'll take moments at point E. Now, if you take moments at point E, that eliminates the need to find EX and EY. That eliminates the need basically. EY, I mean, and we don't need to find those forces. We already know what alpha is. So taking moments at point E is the same as sum of moments at point E is equal to 0. Anti-clockwise is positive. Clockwise, that's positive. Basically, right. So now, if you look, let's take a closer look at the diagram. If we look at this, see, from this is sorry, it's not. Just from this line, from where D is to is the point here where we have C, right? So this point, it's 100 millimeters. From this line where C is up to, let's see, this point up to this point here, it's 450. 450, let's say it's somewhere here. Sorry, somewhere here. It's 450. And then from this point up to the ground, that's to the ground. This is the ground here, this part, right? It's 250, basically, right? Then from the wheel center, from this point of the wheel to this point here, it's 500 millimeters. And then from this point where E is up to where C is here, it's 675 millimeters. Now, the idea with these numbers is easier to kind of put things in perspective. And also, your free body diagram is not complete. You should have represent the forces and the distance. It has to be shown on the free body diagram. That's what we have there. So now, in finding this, we already know we're taking moments at E, which is here, right? So the first force we have is this FCD. Now, FCD, you have to represent it in the X direction and the Y direction. Now, for the Y direction, it will be 0 because it's acting on this line of action, right? So you can't take more. There's no turning effect there. It's 0. But for this point here, but for the X-axis, you have to multiply from this component from the X-axis up to this point, the distance, which is 100 plus 450, which is 550. So the X component of FCD, right? X component of FCD X component of FCD, which will be FCD from a trig, you can see that will be cos alpha, right? Multiplied by 550, which is the vertical distance, 100 plus 450, 450, yeah, which is 550. And since it's going anti-clockwise, because it's this force here, you turn this, if you press it, bend it, it tends to bend this, yeah, that way. Okay, no, actually, so for this force, the moment you try to bend, it tries to go anti-clockwise. That's why it's positive. Sorry for that. But then this reaction force here, it's up and this way. Then if you apply force, it's bending, it's going the other way. That makes it negative. So that would be minus R equals to, now what's the distance between R and where you have the force? I mean, that's where we are taking moments at. That's from this point R here to 500. I mean, sorry, R here to this point here, right? 500. So the effect of the turning effect of the force is what determines the sign. So that's R equals to 500. I mean, that's R times 500, sorry, equal to 0. So if you simplify this out to be, let's see now, FCD, remember alpha is, if you scroll up to our ellipse, 8.427 degrees, right? So it's FCD. If you take this, if you move this to the other side, because you should, I mean, you should be able to, you know what R is already, right? If you multiply R times 500, R times 500, move it to the other side, then you divide by cos, and divide by cos alpha on 550, you'll be able to get what FCD is. So that would be 500 times 2654.5 divided by 550 cos 8.4270. So FCD is equals to 2439.5 Newton. Now, let me verify this. So it's 500 times 2654.5 divided by 550 times cos 8.4270. So we get 243, that's 2439.5 kilonewton. Now this FCD, if you look at the forces here, where is it? You have a force, I mean, this is the direction here, right? So in the turning effect of this is the fact that this force, remember, this force acts at this point here because it's assumed that, where is this? Let's assume you're pulling this way, right? This one has to keep the ticks on the ground here, right? So the direction of this is FCD. It's facing that direction. So we have one component here and one here. I mean, yeah, one component here. The other one should be there. So this FCD already is negative, right? So that's the so the sorry. Yeah, okay, write it here. Compressive force. Alternatively, you could put the negative sign here already. So that negative sign will be here, then here. So it's a compressive force, basically. So that's the force in CD, which is this is CD. However, the question is not asking for the force, it's the normal stress in the rod. So of course that is the force over the area. So that is stress in CD will be the force CD over the area. Now we already have the force as negative 2439.5 divided by the area. Now they said the rod, we already have the diameter of the rod from the question. The question says a steel rod, connected by 25 millimeter diameter steel rod already. So we know that's the diameter. So the area is pi d squared. So okay, this is in Newton. So and that's the 25 millimeters, right? You have to convert this. You have to convert this to meters. Right? That's 25 divided by 1000, 0.025. That's it in this diameter. So pi d squared 25 squared over 4. That's the area, or you can say pi r squared. That would be pi 0.0125 squared. Either one works. So the stress will be the stress on the CD member, or that component would then be. You remember we have it's negative because the force is, as we had shown there, so it's negative. Right? So minus 49697 times 10 raised to the power 6 Pascal. However, since we have 10 to the 6 here, we can convert that to megapascal. So that would be minus 49697 megapascal. CD equals to this. To the required decimal place is 4967 megapascal. And that is the stress in that member. So just as a recap, what we have done here, first we took the free body diagram of this, analyzed it, and got the reaction force. Secondly, we took we then made the free body diagram of the arm and wheel unit. Of course, we took one of that here, which is this one, and we analyzed this here. Took moments about point E. Taking moments about this, we didn't bother about these forces here. We already have the reaction force from here, and we also had this force FCD is what we are looking for. The vertical component, since it acts along this point of action, it's 0. We didn't need to compute that. But then for the X component, which is FCD cos alpha, we then multiply that by the vertical distance, which is 450 plus 100, which is 550, then times the reaction force, which is from this point here, acting to this line of action here. So, and with that, we're able to compute the force, which is a compressive force, right? But if you look at this, it's acting here, this way, compressive. I mean, because if you resolve this one, it will be resolving into one direction here, and that direction as well, too. So that compressive force is what is this. Now, of course, the question did ask for stress. So we don't compute the stress by dividing the diameter we have by pi d squared over 4 pi r squared to get the stress in CD component, which is negative or minus 4.97 MPa. I hope this helps. Cheers.